The rubber duckies of the North Pacific. My name is Rowan, and I'm going to lead a presentation on surface currents. So before we get to the rubber duckies, we have to talk about these surface currents and how these start with surface winds. On this diagram, you can see the air circulation cells, which form from the heat rising off of the equator, creating these cycles, distinct from different lines of latitude, 30 degrees, 60 degrees, 90 degrees. And we can see that these surface winds are the winds that, of course, hit the surface and are on the bottom of these air circulation cells. And as you can see across the equator, they mirror each other and go in inverse directions. So we have these surface winds, but what you'll notice on this diagram is that these winds actually end up curving. This is because of something called the Coriolis effect. The Coriolis effect is when Earth's rotation and speed differences across different lines of latitude, across the curvature of the Earth, causes a deflection in water and airflow. And what you'll notice, because of the Coriolis effect, is that north of the equator, the air deflects right of its intended path, and south of the equator, it deflects left. And that is the reason for this curvature. Next, we're going to talk about how surface winds affect surface currents, so air to water. As you know, or may know, if you are drinking water and blow onto that water, the water will tend to go in a similar direction as the wind. However, because of the Coriolis effect and something called Ekman transport, the movement of water does not follow the same path as the surface winds. So here's a diagram that is a way to visualize that in the Ekman transport. So let's imagine this is north of the equator. Here we have the flow of the surface winds, or in this case, let's say the northeast trade winds. Because of the Coriolis effect, the first utmost layer of the surface current is deflected slightly, about 45 degrees. This current is pretty strong because it absorbs the most energy from this surface wind. But in Ekman transport, it describes the surface of the ocean as in several layers. So below this utmost layer is another layer, which is deflected even more from this utmost current. As you can see, this arrow is also smaller, which represents that the force is weaker. And we can continue this sort of process as this energy gets deeper and deeper into the surface current layer. So eventually, it just keeps on deflecting and getting weaker until it's actually going in the opposite direction as the initial surface wind. Taking this sort of spiral into account, Ekman transport describes this net current of water as moving at a 90-degree angle of the initial surface wind. And something to remember is that this current is going 90 degrees right of the surface winds in the north. So vice versa, in the south, the net current would go 90 degrees left of the surface winds. So if we put this on this diagram, we can see that with this deflection, the net current of water, the surface current, goes sort of horizontally west. So, knowing how these forces work, we can tie them together and apply them to the North Pacific Ocean. The surface current that I described earlier is called the North Equatorial Current. As you can see, further north, these orange arrows represent surface winds called the westerlies, which, because of the Coriolis effect and Ekman transport, also form surface currents which deflect right and move toward the west coast. When these two currents collide with the surrounding continents, most of the water ends up flowing into the previous current, creating a cycle called the North Pacific Gyre. Additionally, you can notice that some of the water goes up north to Alaska, which is called the Alaskan Current. The Alaskan Current also feeds into another gyre called the subpolar gyre, which I'll get into in the next slide. Now, finally, how do rubber duckies tie into this? So, in an article provided by Treehugger, roughly 28,000 rubber duckies were accidentally let loose on a shipment from Hong Kong to the US. Around the globe, hundreds of people found these rubber duckies wash upon their shores. In the article, they provided a map of the duckies' journey across the world. And I'm sure you guessed by now, but these rubber duckies follow the path of surface currents. If you dropped a rubber ducky into a river, you can imagine that the duck will follow the stream. For this reason, many of these duckies followed the path of the North Pacific Gyre. After all, surface currents are basically rivers in the ocean. Some duckies ended up even further north, following the path of the Alaskan current, and even circulating around the whole subpolar gyre, and ending up in Tacoma. Other duckies even landed all the way in the Atlantic after several years of drifting. But what we can also see about the path in the Pacific is that some duckies, in addition to following the path of the North Pacific Gyre, also ended up further south. The duckies that ended up in Indonesia were likely guided by the North Equatorial Current, and it's likely that some duckies ended up in the South Equatorial Current, and eventually into the South Pacific Gyre. As you can see, the South Pacific Gyre goes counterclockwise, whereas the North Pacific Gyre goes clockwise. Because the Coriolis effect is a main factor that creates both of these currents, and the Coriolis effect goes in opposite directions across the equator, this makes sense that these gyres were essentially mirror images of each other. So, by following the South Pacific Gyre, some of these duckies ended up landing in Australia and Chile. Thank you so much for listening, and here are my sources.